Okay, this section is section 7.7, and this time we are talking about something called the base e and natural logarithms. In the last section we talked about common logarithms, and we talked about how a common logarithm is written without the base, even though we know that there's a base 10 there. Today we're going to talk about another frequently occurring logarithm, which is called the natural logarithm. But to talk about what a natural logarithm is, we have to talk about the natural base, which is a number that we call e, and then we're going to review or use our same properties of logarithms and solving to solve exponential equations and inequalities that involve the natural log. So the vocabulary you need to be on the lookout for is natural base e, a natural base exponential function, and then a natural logarithm. So the question that we need to answer is, what is the natural base e? So this number e is called the natural base. E is a special number. It comes up a lot in math and science. It also comes up in interest, as we're going to see in this section. It comes up in exponential or particularly radioactive growth and decay, like continuous growth and decay. E is an irrational number. So it's just like pi. We know that pi is a number. It's 3.14 and so on. Goes on forever. Or the square root of 2. We know the square root of 2 is an irrational number. Sorry that this keeps freaking out. And e is also an irrational number. So when you see e in math, it is an irrational number, and its value is 2.71828 and so on. Remember, irrational numbers go on forever without repeating. And if I have an exponential function that has a base e, so if I have log base e of x, right, I call that the natural base exponential function. All right, take a look at this slide here. Be careful, we're going to talk about exponential functions that involve e and logarithmic functions that involve e. So f of x equals e to the x is continuous exponential growth. E to the negative x is continuous exponential decay. And when I take the inverse of the exponential function that has the base e, I get a logarithmic function with base e, log base e of x. But this is important. Instead of writing log base e of x, we usually abbreviate it as ln, natural log of x. So log base e of x is equal to ln of x. So when you see ln of x, you should think log base e of x. And here, they're just showing you how the natural log of x is the inverse of e to the x, just like the other exponential and logarithmic functions that we have seen. Okay, so we are going to practice here going back and forth between exponential form and logarithmic form with e. So if I have e to the x equals 23, its exponential form, I want to write it in logarithmic form, just like we did at the beginning of the chapter. The base of the exponent becomes the base of the logarithm. It's equal to the exponent, and the 23 is inside the log. So log base e of 23 equals x, but we don't leave it as log base e. We always write log base e as ln, natural log. So log base e of 23 is ln of 23 equals x. Same thing for e to the fourth equals x. I'm going to rewrite it as log base e of x equals 4, but I don't leave it as log base e. I replace log base e with ln of x equals 4. Okay, so here are two for you to try. E to the x equals 15 in logarithmic form should look like ln of 15 equals x. Log base e of 15 equals x is how you would start, but you replace log base e with ln. All right, try this one. Okay, in this case you get ln, or the natural log of x equals 4. Remember, that's the same as log base e of x equals 4, but you have to write log base e as ln. Okay, we're going to continue. This time we're going from logarithmic to exponential form. So I know that ln of x is the same as log base e of x, right? So just like we've done before, I take the base of my logarithm to this exponent is equal to whatever's inside the logarithm. So I get x is approximately e to the 1.2528. Same thing here, natural log of 25 equals x. Remember, natural log is log base e, so if I want to write that in exponential form, I get e to the x is equal to 25. Again, this is just review. This is exactly the same as it was back in section 3 when we first learned about logarithms. It's the same as it was with common logarithms. The process is always the same. You just have to recognize that ln means log base e. So try this one. All right, you should have gotten x is about e to the 1.5763. And try this one, please. All right, for this one, you should get e to the x is equal to 47. All right, now we're going to talk about simplifying expressions. Again, in this section, we are using the same logarithmic simplification that we learned way back in section 5. So I have 4 times natural log of 3 plus the natural log of 6, and I want to write it as a single logarithm. So 4 natural log of 3 becomes the natural log of 3 to the 4th, because remember the coefficient becomes the exponent. And then, since here I have the sum of 2 logarithms, the natural log of 3 to the 4th plus the natural log of 6, that becomes the single logarithm of the product, 3 to the 4th times 6, which is 486 if you multiply that out. And we can use a calculator to verify the solution. Your scientific calculators, just like they have a log button for common logarithms, they should also have an ln button for natural logarithms. So you would be able to check the answer that we just got and see if it was right. All right, part B, we're going to write this 2 times natural log of 3 plus the natural log of 4 plus the natural log of y. We're going to condense it into a single logarithm. So first, I'm going to take the coefficient of 2. It's going to become the exponent of the 3, so the natural log of 3 squared. And then all of these are added, right? Separate logarithms added, so it becomes one logarithm, which is the product of what was inside each of the logs. 3 squared is 9. 9 times 4 gives me 36 times y. So I have the natural log of 36y. Okay, I want you guys to try these. Write this as a single logarithm. Your answer should be D, the natural logarithm of 48. And here's the work for that. Try one more. For this one, you should have gotten B, which is the natural log of 9x. And there's the work for that one. That's how you get B. All right, now we're going to be talking about solving equations with base e. So these equations are exponential. There's no logarithm in them, but they are exponential. I don't know why it's erasing itself, but that's okay. We're going to solve 3 times e to the negative 2x. That's how I can tell it's an exponential equation, because the variable is in the exponent. Plus 4 is equal to 10. So we're going to start by subtracting 4 from each side. So that's where we get the 6. Subtract 4. Then I'm going to divide both sides by 3, because this 3 is not attached to this negative 2x exponent, right? It's just multiplied by the e. So we divide by 3 to get the e with the x and the exponent by itself. And now we're going to use logarithms, because remember, when I have an exponent that has a variable, I need to use a logarithm to take it down. But anytime I have e as my base, I should use the natural logarithm of both sides. So since the natural logarithm is log base e of e, those undo each other, those are inverses, so I'm just left with negative 2x is equal to the natural log of 2. That's going to be a number. We don't know what it is yet. And then I divide both sides by negative 2. And then you would use a calculator to get this value and round it to the nearest 10,000. So if you use a calculator, you would plug in natural log of 2 divided by negative 2, and you would get negative 0.3466. All right, I want you guys to try one, please. In this case, your solution should have been A, and there's the work if you need to pause and write it down. Okay, this time we're going to solve equations that actually have the natural logarithm in it. So here we have 2 times the natural log of 5x is equal to 6. So first we need to isolate the logarithm. So I'm going to divide each side by 2. So I get the natural log of 5x is equal to 3. And then anytime I have a natural log, it's really easy to take e to both sides, or basically you can think about, well, there's two ways to think about it. One is I'm taking e to the power of the natural log of 5x and e cubed. When I do that, the e and the natural log undo each other because they're inverses, and I get 5x equals e cubed. Remember that e is a number, not a variable. And then I divide by 5 on each side, and I would use a calculator to get the answer. Another way to think about what I did here is to think about rewriting it in exponential form. So instead of taking both sides, e to both sides, I think about this as log base e. So I would just rewrite this as e cubed equals 5x. I would just rewrite it in exponential form, and then I get to the same place, and I continue by dividing by 5. All right, here's an inequality. The natural log of the quantity of 3x plus 1 squared is greater than 8. So remember that for inequalities, we have to be careful with what's inside the logarithm as well. So I'm going to take e to both sides here again, like we did in the last one, and e and the natural log are inverses, so they undo each other. And I get 3x plus 1 quantity squared is greater than e to the 8th, but they're rewriting e to the 8th as e to the 4th. Because if 3x plus 1 squared is greater than e to the 4th squared, what's inside the squared, or 3x plus 1, has to be greater than e to the 4th. Basically, we took the square root of both sides. Then we subtract 1 from both sides. Remember, e to the 4th is just a number. I'm still isolating the x. And then I divide both sides by 3. And then I would use a calculator to get this and round it to the nearest 10,000th. Notice we're normally rounding to the nearest 10,000th, which means I'm rounding to 4 places after the decimal point. And since it's a greater than inequality, we don't have to worry about it giving us something in our original inequality that would not work. If I plug in 17 point something into here, it's always going to be positive, especially because I'm squaring it. So I don't have to worry about any zeros or negatives being inside of my logarithm. All right, try this one. Your answer for this one should be C. And there's the work. We divided both sides by 3 first, and then I showed you both ways, either rewriting it in exponential form or taking e to the power of both sides and going from there. Either way, you get the same result. And let's try an inequality. All right, the answer here is A. And here's the work. Again, 2 ways. I can either start by taking e to both sides, or I can start by using the property of logarithms and rewriting this in exponential form, remembering that what's inside the logarithm has to stay on the left, and the exponential part, e to the 7th, has to go to the right. Okay, the last part of this section is something called continuously compounded interest. This is a specific application of the number e. So A is still the amount in the account, P is still the principal, how much I start with, how much money I invest, and R is the interest rate. And t is still the time. But notice that the r times t is the power of the number e. So if we take a look at some examples here, I'm depositing $700, so that's going to be my principal, into an account paying 3%, that's my rate of annual interest, compounded continuously. When you see that word, that tells you you need to use the formula we just looked at, P times e to the RT. And I want to know the balance after 8 years, so that would be my time. There's my continuously compounded interest formula. So I plug 700 for E, 0.03 for R, remember we turn percents into decimals, times 8, and then we just use a calculator to simplify. So I get about $889.87 after 8 years. That's how much would be in my account. Here's the same idea. I'm depositing $700. I still have 3% interest. I'm still compounding continuously. How long will it take for the balance to be at least $1,200? So that means I want my balance to be greater than or equal to $1,200. So A, my amount, which I represent with P times e to the RT, needs to be greater than or equal to $1,200. So I'm going to divide both sides by 700. And then I have e to the 0.03t. So to get that variable out of the exponent, I take the natural log of both sides. and then divide, and I get 17.975